So this is more in a structured manner. The three steps have been defined. So you have the pre-processing, and we have the solver execution, and finally we are doing some analysis. We're going to look at them in a more defined manner now. So first of all, let's define for ourselves what our modeling goals are. This is even before we start with the geometry creation and meshing. So we try to define for ourselves, okay, what are the options available for us? What are the different packages available? That's what we want to learn through this lecture. What are the different options we should look for? So we are going to look at what is the kind of physics involved if we have to put in some assumptions, whether we can simplify a problem. In some cases, when the features are not available within a given software, we might have to customize it. So that's what is meant by customization. So we need to ask these questions to ourselves. Once this is defined, we look forward to the timeline and the accuracy. So these are two ends of a stick, so we have to get one of them. So either we have to have an accurate result, but if we go for huge amount of accuracy, we might end up spending a lot of time on achieving that accuracy. So we have to make these decisions before we start with the problem setup and simulation. We also need to ask ourselves, what is the defined geometry? Sometimes your system might be a very big one and you might have to isolate a piece of it. So we have to define what are the boundaries available. Where should my computational domain begin or end? And do I have appropriate conditions defined at those places? And we also try to ask ourselves whether we can simplify the problem as a 2D problem or an axisymmetric problem. Most of the problems nowadays that we encounter are not of this class, but nevertheless these options should be also available, and we should accordingly decide which software program we should look forward to. Once that is defined, maybe you will remember this image. We have spoken about how the computational domain has to be extracted from the physical domain. So we have a big geometry available here of a fin tube heat exchanger, and we take a part of it as was defined earlier. So that's where we define the domain. So the domain begins and ends at this diagram which is shown on the right hand corner. So this is how we try to define our model, our computational model. And once the domain is defined, we start meshing it. That's when we try to discretize our geometry. Once the geometry is discretized through triangle, quadrilateral, if it's a 2D problem, or tetrahedron or hexahedral meshes, in some cases in fluid mechanics especially, we might also need a good prism layer mesh. So we also may have to have features where you can also include prism layer mesh. So these are the kind of questions we try to ask ourselves. Basically, most of the commercial packages nowadays can handle all kinds of mesh. Nowadays, it's also getting more popular is the polyhedral mesh, which is available in ANSYS products in Fluent, but also in Star CCM Plus. Star CCM Plus were the pioneers in introducing commercially within their Star CCM Plus framework. They introduced the prism layer meshing, which is now also available in Fluent, and basically such tasks can also be done in ANSYS Fluent now. Once our meshing is done, we start designing it. We try to, once we have decided what mesh we have to use, we start creating the mesh, and we try to have a mesh which can resolve the physics involved, which can also be small enough that a computer can handle it and solve the equations. So we have to ask ourselves whether we can afford to have a huge cell count, because huge cell count means a huge computational effort. So our computer, our hardware requirements are also competing with the amount of cell count that we can handle. So there are different kinds of options. We have try or det meshes. You can see some domains which have been meshed using hexahedral elements or tetrahedral elements. And we can also have a hybrid mesh, so we can have hex mesh in some areas, and we can also have a tet mesh in the other area where it is difficult to generate a hex mesh. Once the meshing has been done, we start setting up the problem. We try to check the mesh whether everything is fine. We start defining the physics in terms of turbulence model, combustion, multiphase, or other kinds of models. We try to define the material properties. We set up the operating and the boundary conditions, and after initializing the problem and having the appropriate solver controls, we start solving the problem, and we have convergence monitors to help us gauge whether the solution is going in the right direction. And that's when we compute the solution. So we have uh, convergence monitors which help us to predict whether the convergence has been reached. Once the convergence has been reached, we look for accuracy of the problem, and if there is anything to be refined, we go back to the first step, or we go back some steps further back to modify our settings and again get an accurate result. How do we check the accuracy? That's where we have to employ the post-processing features. So we examine the results which have been generated. So we try to find out the forces, the moments. In some cases also, some qualitative analysis is helpful. So we need to be able to predict where the shocks are taking place, where is the flow separation, how much effect it has on the pressure drop calculations. So these are some of the things we try to answer during our simulation at the end through examining the result. So that's where we start analyzing whether we need to revisit some of the settings that we have made in terms of boundary conditions or the turbulence models that have been included, whether we should have included the compressibility effects. So we try to check these kind of problems dependent upon the Mach number. We also try to refine a mesh in some cases. So we can do this through grid adaptation or mesh refinement. And we try to also revisit the boundary conditions. Now that's a general overview of the different components that you can expect in any given CFD software. So any CFD software has a GUI and a TUI, that is a graphical user interface and text user interface, through which the user can have an interface with the software. The user can communicate with the software using these two means. And there are some specific components like options for importing and exporting files from the software. The software should usually nowadays have a model tree, so which defines very clearly what are the steps involved in the given problem. We also should be able to handle the different options from a menu bar, and there are some shortcuts available through a toolbar, everything operated via a mouse. We have a details pane where we can enter details. So this is more or less a combination of GUI and TUI that we feed in some data, and we also use the mouse at the same time. And ultimately, to be able to analyze the results, we should have a graphics window. So that's the components that you can expect from a CFD software usually. So these are some examples we are having. This is a snapshot of ANSYS Fluent. So you have a variety of options here. You have the typical model tree or the tree that I had spoken about. So these are the steps that are to be followed. These are also accessible through the menu bar here, and there are some toolbars available. There are some descriptions, and where you can interact with the software by feeding in the appropriate boundary conditions. For example, this is the text user interface in combination with the GUI. Let's have a look at CFX. CFX also has a similar architecture, so you have the tree available. It's a bit different though, and we have the toolbar, the graphics toolbar additionally, and the graphics window, and we also have the main menu available in CFX. That's a snapshot of Star CCM Plus, which has been taken from their website from one of their marketing videos. So what you can see here is a globe valve simulation which is being performed, and what you can see here is the polyhedral mesh, which is now also available in ANSYS Fluent since the 6.3 release. But Star CCM Plus was the first to introduce it. So you can see a prism layer mesh, the fluid domain which has been extracted and meshed using polyhedral elements, and with the prism layer additionally. And it also has a tree structure, and you can also feed in some details to the software using some panels where you can feed in some data, and some what is the progress is reported in this window here. So that's a snapshot of Star CCM Plus. Basically, if you look at the different codes that are available nowadays, we have a variety of codes which are also open source, or at least which are free. Um, the idea behind open source is to democratize the usage of software programs. So we have codes like OpenFOAM, which is the most popular one here in this list. We also have some other academic codes and research codes for multi-phase simulations called MFIX. we have Code Saturn, and actually if you visit this website CFD Online, this specific link, you can get a variety of freely available CFD codes which you can at least use. You can usually perform also a commercial business with them. Some software only encourage them to be used for academic purposes, but the idea behind open source software is the following. Usually there is no licensing or upgradation costs. If you want it specially customized, of course, then you have to pay, and they would do it especially for you in that case, some customization. But basically, there is no licensing or upgradation costs. All that you need to pay usually is for support and services. So if, let's say, through this course, if you are very well familiar with CFD and you can start handling any of these open source codes, you're done basically. You can do CFD analysis without actually purchasing one of these commercial codes. So you have commercial codes like ANSYS Fluent, CFX, Star CCM Plus, which is from CD Adapco, and we have multiphysics software like COMSOL Multiphysics, which has the CFD features available as well. We have CFD++, which is especially popular in the aerospace sector. We also have Flowtherm and Flow 3D, which is actually more for free surface flows. Flowtherm is more of a domain specific software for electronic cooling, and AccuSolve, which can be used for design of experiments. So you can do a lot of simulations using AccuSolve. What you don't see on this list is something called CF Design, which has recently been taken over as a product of Autodesk. So now it's a product of Autodesk, but basically you have a variety of codes which are available. You can again visit CFD Online, the link which I had given you earlier, which also lists these commercial software packages which come with a licensing cost and also upgradation cost. So if you want to upgrade the software, you have to constantly pay an annual maintenance cost. That's called the AMC. A part of the support cost is also included in the AMC, but sometimes if you want customized support for yourself, in that case you have to additionally pay for the support and services. So there are some limitations in commercial CFD codes, that it's only possible, only affordable, usually not for individuals but for big enterprises. But there are many more features in terms of support and software features which are available with the commercial CFD packages. So just to summarize the overall problem, you can see we are having a huge variety of CFD software products, both open source or free software packages as well as commercial ones. Usually what you're looking for when you're looking for any CFD software, you should ask yourself or ask the software person, the responsible person, for the following questions. You should see whether it is especially customized for your specific application. So if whether it is specialized in your domain or what all features it has. That's the first question. We should also ask ourselves whether the software is robust, whether it will crash, or whether it will be able to solve the problem, at least achieve some amount of convergence. Once that is resolved, we are looking for the accuracy of the simulation. So we are looking ultimately that the CFD results should match with the experimental ones. In all these things, we are also looking for quick solutions. So the competition is very cutthroat, so people are looking for very fast and quick simulations. And ultimately, we should be also able to couple the given software, given CFD code, with other codes like structural mechanics software, or let's say optimization software. And that speaks about the interoperability of your given CFD code. And as we have also seen, there are more means of customizing the given software, but that is all a bit more specific. Usually, if you learn one of the given CFD codes, either commercial or open source, you can usually shift very smoothly to the next one. So that happens very often, that you are working in a specific company on one given CFD code, and then you go to another environment where they have different licenses. Usually the transition is smooth, but you have to understand the language of that specific software. But the basic things which have been covered in this lecture remain the same, and it's usually the experience which counts more than having the know-how or the savoir-faire of a given special software. ANSYS Fluent and ANSYS CFX are very popular in the industry in India as well as abroad. Star System Plus is a very close competitor for them, and we have many other codes which are available, which usually try to reduce the effort required for the user. But having learned on ANSYS Fluent, um, this overall CFD process, you can usually shift to any other software very smoothly and easily. So this was all about this lecture, having a software perspective of CFD analysis. I hope you could follow how the CFD software process works when we are looking at it from the point of view of a software. What are the things to be expected and how we can use the given software for our specific purpose for performing the simulations for product design. More information you can find on our website, and any queries can be directed to the contact which has been provided here. Thank you very much for your attention. Stay tuned for the next ones.